Hey everybody, my name is John Palucci, and this is a lecture on bullet ricochet phenomena. Hopefully this will help you in responding to, processing, and analyzing crime scenes, in determining directionality and other characteristics of a bullet ricochet mark. Essentially, what you're going to see is from work that was done by Ed Heesky, which is in this book, Practical Analysis and Reconstruction of Shooting Incidents. I contributed a minor part to this textbook. Uh, Mr. Heesky was my teacher and my mentor, and he's also we've done shared casework together and done peer reviews for each other in my current capacity. So, what is a bullet ricochet? The results of a bullet impacting a surface or an object at an angle of less than 90 degrees and thus being deflected off in a different direction and or angle. So how does a ricochet happen? What are the ultimate optimum conditions for producing a ricochet? The preferred bullet is a large, slow moving bullet. So think about a 45, right? It's not a function of high velocity because high velocity bullets have a greater tendency to fragment upon impact. So a 223 versus a 45, and a 223 would be approximately 3,000 feet per second and versus 850 feet per second for the 45. So upon impact with a target, the 223 often fragments while the 45 will ricochet rather than fragment. So what types of conditions are we looking for? What types of substrates and things will that help us cause a ricochet? So it could be produced by virtually any surface or object under the right conditions, any surface, including the surface of water. And what conditions are required? For every surface material, there is an angle at or below which a ricochet can be expected for a given bullet. This angle is known as the critical angle, okay? So the critical angle is very important to know. It's dependent on the bullet configuration, the cartridge type. If you're looking to reconstruct this, you have to have very, very similar conditions. You might even want to try the same substrate as the ricochet mark that you're analyzing. Okay, so this is known as the critical angle. So it's the angle at or below which a ricochet will occur, right? So we'll talk a little bit more about critical angle. So say I'm trying to create a ricochet off of the hood of a car, and I'm firing a 45 ACP Colt 1911 with a 4-inch barrel, and I fire and I have a round nose bullet, and I fire at the hood of this car at an angle of say 70 degrees, and the bullet goes through the hood. It doesn't ricochet off the hood, it penetrates, right? So now we make the angle a little more shallow, right? So let's say we try 60 degrees, and still it penetrates or perforates the substrate, the hood of the car. So we'll try 50 degrees until we find the angle at which that bullet is going to ricochet. So say that the angle is 45 degrees. So from 45 degrees down to just about zero, you're going to create a ricochet. That is our critical angle, is 45 degrees. If we go above 45 degrees, the bullet's not going to ricochet. Instead, it's going to go through our substrate, right? Or the hood of the car, which would be the substrate in the example I'm giving you. So how does bullet design affect ricochet? The bullet design has a significant effect under certain conditions. So a semi-jacketed bullet with an exposed lead nose will behave significantly different when striking a surface, such as an automobile windshield, as compared to a full metal cased bullet, like a military ball. The full metal cased bullet will have a greater tendency to ricochet at a given angle of impact. So the angle of impact versus the critical angle. What's the difference between those two? The angle of impact is the angle at which a bullet strikes a surface. That's period right there. Critical angle is the angle at or below which a ricochet will be expected for a given surface and bullet. Okay, that I just explained to you. So what happens if the angle of impact is greater than the critical angle, right? As we talked about, over 45 degrees, we're going to have penetration resulting. How can the critical angle be determined? Typically only through test firing with the weapon and the bullet in question and the particular substrate. Okay, so you can't just go and say, all right, this was the hood of a car. Hey, let me get this quarter panel from a truck, and well, I'll use something like a Derringer with a inch and three-quarter barrel and 45 long Colt versus 45 ACP. So you really have to do your homework on if you're going to reconstruct this, the cartridge type, the weapon type, and the substrate. So you really want to recreate those conditions. Are there any published studies? Yes, there have been a number of studies published in the AFTI journal and other forensic publications on bullet ricochet phenomena. So what is the ricochet angle? It's the angle of departure of the ricocheting bullet. Okay, so here, let's pretend that over in this area right here, this is where your gun's being fired, right? So this is the bullet exiting the muzzle, and it comes down and it strikes the surface, right? That's your angle of impact, the angle at which the bullet strikes the surface. Now the bullet strikes the surface, it might travel down the surface a little ways and then decide to depart, depending on the configuration of the bullet and all those variables that we talked about in the substrate type and all that. So here we have an angle of impact, and then a bullet departing the surface at a lesser angle. You can see this is a greater angle than this angle right here, right? So that's our ricochet angle. So we have our angle of impact, we have a critical angle, and we have a ricochet angle. Now let's look at this plane here. So angle A is our impact or our incident angle, right? So here we have the shot fired, travels down, strikes a substrate, right? Travels along the substrate a little ways, and then departs, right? So now we have actually the angle of departure, right? Which is this angle right here. Right? We also have a lateral or deflection angle, right? You can see here's our impact point, here's our departure point. So we're going to get much better graphics to talk about the lateral or deflection angle. But what happens is, typically, depending on the substrate, the bullet also what's being fired. Is this fired from a barrel with no rifling in it? So we know about rifling, right? That the rifling in a barrel will cause a bullet to spin in a particular direction, which would be either left or right. So if we have here a bullet that has a right-hand twist, it's being fired from a barrel with a right-hand twist. So the bullet is spinning to the right-hand side. We'll have our angle of impact, right? The bullet's fired, strikes the substrate, travels along the substrate, departs. This is our ricochet angle. We will also have this lateral or deflection angle. So if the bullet has right-hand rifling, right? It's fired through a barrel with right-hand rifling, it's spinning to the right. The bullet's going to actually deflect off to the right, so it won't be a straight line. Where it's fired, it hits the substrate, travels along the substrate, departs in a straight line. Typically, the rifling will have an effect on it as well. So the angle of impact versus the ricochet angle, right? How does it compare? For most surfaces, the angle of ricochet is less than the angle of impact, as we saw in that graphic before, right? When the bullet departs, it's a lower angle. So something like steel, concrete, or asphalt could be if the concrete and the asphalt are pretty solid, they're not the type that break up very easily, right? Which we would call frangible. What are some exceptions? Notable exceptions are water and sheetrock. So the ricochet angles for these and similar surfaces are usually greater than the impact angles. So with sheetrock and similar surfaces, right, here we have our angle of impact. And if you look at this angle, it's actually less than the angle that the bullet's departing at, which is the ricochet angle. So why does this happen? Probably due to the hydraulic effect of the water and the buildup of material with sheetrock. So I'll tell you a quick story about when I was recreating this. At a class I was teaching, we were at a range, and I took two pieces of wonderboard. It's like that cement. It's like a sheetrock, but it's like almost like a concrete, and you use it for bathrooms. And I took two pieces and I glued them together, and I put them down on some sawhorses, and I fired a 45 round nose into it at about like a 15-degree angle, very low angle. And this bullet took off all the way up on top of a berm. So what's happening is when the bullet strikes the surface, it's dislodging some material. That's been called spall, S-P-A-L-L, in some teachings. And the spall sort of builds up and creates a ramp, right? So the bullet comes down, strikes the surface, dislodges this material, which then creates like a ramp for the bullet to take off up that ramp. Okay, so that's why that can happen with frangible surfaces like sheetrock, the wonderboard. If you have an asphalt that's in really poor condition, that will easily break apart when it's struck with a bullet. Also with water, you know, if you think about it, when it strikes at the critical angle or below, and it creates almost like a wave when it strikes the water. Think about jumping the wake while you're water skiing, right? That's pretty much what the bullet's doing. It's jumping over the wave created by the impact and taking off at a higher angle. So when you're, you know, vacationing on the lake and having a few Heinekens on the porch, and decide to pull out the 45 and have some fun, just, you know, if there's any other cabins anywhere near that place, don't even think about it, because that bullet could really take off from the surface of the lake. Okay, here's an example, very, very low impact angle, right? So the bullet comes in almost at the level of the water and starts to take off. Okay, as you can see, it's kind of an old graphic. So that was a 22. So ricochet from water, any of these surfaces, right? We have a very low impact angle, and it starts to take off at a greater ricochet angle. So here it is for your enjoyment and entertainment. We have a hard surface. This is your angle of impact. This is your ricochet angle. A hard surface will have a low ricochet angle. Okay, semi-hard surface could have a greater ricochet angle. And a very soft surface, like we just spoke about, will have an even greater ricochet angle. Here's some bullets that were ricocheted off of plywood, right? So we have the ricochet marks and we have the bullets. You can see if you look at these two right here, right? There's all this fouling on this bullet, and this one looks pretty clean. So what happens is the bullet comes in, it strikes the surface, and it transfers all the soot and fouling that's picked up as the bullet travels down the barrel. It transfers that onto the substrate, the initial target that it strikes, right? We'll call that a bullet wipe. So if you look at these, you can see a very symmetrical sort of lead-in mark, or shoulder, depending on what kind of surface we're talking about. So the bullet strikes here, travels down the plywood, and then departs, right? Here we have it again, much bolder. We can see the transfer of the soot over here. So the bullet strikes here, ricochets off in this angle, right? And what would make one mark longer than the other mark? Probably the incident angle or the angle of impact, you know. So a lower, when the bullet's fired at a lower angle, say this is 15 degrees, right? Now this one's actually says here 8 degrees, right? And it'll travel along the surface for a longer period, right? So we're going to call those lead-in marks right there. Here we have the bullets, and you can see the soot wiped off of them. This photo here is courtesy of Lucian Haig. It's another sort of Bible on shooting incident reconstruction by Michael and Lucian Haig. So this has the lifting phenomena, right? Sometimes when you have like a laminate, you have multiple layers. You can see how this layer right here is lifting off of the lifting away from the rest of the surface. So what we have here is a way for you to determine, one of many ways for you to determine where that point of impact was. And what can you tell once you have the point of impact? Well, once you have the point of impact, then you know what direction the bullet's traveling in, correct? So if this is the side, if you have a long ricochet mark and you know which side the bullet struck, then that gives you the direction it was going. So obviously the bullet in this slide was traveling from right to left. So what are some of the other ricochet characteristics? Ricochet directions are pretty much unpredictable. Okay, it's important to remember. Ricocheting bullets fired from weapons with barrels having right twist will tend to deflect to the right, and vice versa for left twist barrels. Okay, here I have two bullets. This is from some experiments that I did. And you know how in the C.S.I. TV shows, they look down and say, oh, this got 8 lands and grooves, and it's a right-hand twist. Well, I don't know if you can look at a bullet laying on the ground and determine how many lands and grooves there are, but what we can do is from these rifling marks, if this bullet's sitting on its base, right, standing up, and the lines from the rifling marks are leaning to the left, it was fired from a barrel with a left-hand twist. If it's leaning to the right, then it's fired from a barrel with a right-hand twist. These are what we call class characteristics. So let's talk about a shoe, right? If there's an imprint in mud and you're a footwear examiner, you might be able to say, well, this is from a Nike Air Jordan. Maybe even determine a size, who knows? But you can't tell me it was mine. If I'm the defendant, you can't say it's mine, right? But you can say these class characteristics will tell me that it's the same manufacturer as the defendant's shoe, right? But it can't tell me it's mine. But now if I walk really funny and I step on a bunch of glass and I put all these what we call accidental markings all over the shoe and I create that same impression, then an examiner could look at it and say, it's the shoe that John Palucci was wearing. Okay, so that's a big difference right there. But here, what we can do at a crime scene is we can look at these rifling marks and determine if it was fired from a barrel with a left-hand twist or a right-hand twist. Now, if you look up general rifling characteristics, you'll see that left-hand twist is much more uncommon than right-hand twist. The majority of manufacturers use a right-hand twist when they rifle the barrels of the guns that they're making. Okay, so sometimes if you go to a crime scene and you see a left-hand twist on a bullet, that right away can eliminate numerous firearms that could have fired the gun, especially with police-involved shootings, because everybody's carrying the same firearm. And if you can get something right away that differentiates the fired bullet from a bullet that would be fired from the police officer's weapon, then we can start making some progress pretty quickly. Okay, so that's very important for you to know, is looking at these lines from the rifling marks and determining, does this have a left-hand twist or a right-hand twist? Now, what can the ricochet mark tell you? It depends on the substrate, right? So certain ricochet marks are going to resemble these here. Right? Now, what can this tell us? Look at this mark, right? So we have a more symmetrical area here, and then it sort of feathers out into nothing, right? But there's a little bit more mark on the right-hand side than there is on the left-hand side. So picture this whole thing, if it was to continue, right? We're missing this area right here on the left-hand side. So there's more of the mark on the right-hand side than on the left-hand side. Same here. You see the symmetrical point of impact, and then we have this area right here. There's more of the mark on the left-hand side than there is on the right-hand side, okay? It's kind of hard to visualize that sometimes, but think about it. If this area right here, right, this end of the mark was extended out, right, it would be shaded in this area right here. Same thing with this one. If this whole area here were extended, this area would be shaded as well. So what we're seeing is a bullet's impacting a surface and it's leaving more, it's having more contact with the surface on the left side in these two than it is on the right side. Of course, these, it's having more contact with the surface on the right side than it is on the left side. See it here? Left side, it's missing on the right side. What's going on here, right? So what's that telling us? This is the drawing of the mark. So what happens is the bullet strikes the surface, and of course the bullet's spinning, right? This is fired from a barrel with a left twist. This is a right twist. So the bullet strikes the surface, a portion of it flattens out, but it continues to spin, right? Strikes the surface, continues to spin. So as it's spinning and creating this mark, now part of it is flat, so you're getting more mark on the right side than you are on the left side. There's nothing here, right? So the bullet strikes here, flattens out the bottom, continues to spin, and it feathers off in this direction, and then the bullet departs the surface. So we have two things going on here. We have our point of impact, which gives us our direction of travel. And we also have more mark on the left-hand side than we do on the right-hand side. And over here, we have more mark on the right-hand side than we do on the left-hand side. So this ricochet mark is telling us that the bullet that created it was fired from a barrel with a right twist. And this one is telling us that the bullet was fired from a barrel with a left twist. Okay, so let's have a look at these right here. So orient the ricochet mark so that it's going away from you as you look down on it, right? So here, these are going away from us. They're going in this direction. Well, basically from bottom to top, right? So the bullet struck here, traveled down the surface. Less of the bullet's in contact with the surface over here on the right side than it is on the left side. So there's more mark on the left. This is a bullet with a left-hand twist, right? More mark on the left. This is a bullet with a left-hand twist. More mark on the right. This is a bullet with a right-hand twist. Okay, essentially you just draw a line right down the center. Where's there more mark? Right here. All right, draw a line right down the center. Where's there more mark? Over here on the left, same here. Over here on the left. Where's there more of the mark? Here on the right. Okay, right twist, left twist, left twist. Sometimes they're a little more stout, these marks, right? But you can do the same thing. Just draw a line right down the middle. You got more on the left. Draw a line right down the middle. You got more on the right. Draw a line right down the middle. You got more on the left. Draw a line right down the middle. You got more on the right. So there's a right twist, a right twist, a left twist, and a left twist. That's on steel. Those are marks on steel. And some of the bullets that caused them were recovered. And you can see they're flattened out. Right? See the bullet with the left twist right here? The lines are leaning slightly to the left. Right? So ricochet creases, right? It's important to be able to establish the direction that a bullet or pellet was traveling when it produced a ricochet mark or crease. What's the difference between a bullet and a pellet, typically, right? A bullet's fired from a rifled barrel, where a pellet would be something out of a shotgun, maybe firing double-aught buck, or you'd have a pellet making your ricochet mark, right? So that wouldn't be rifled. So ricochet crease, here's another way that we're going to determine direction of travel, which is very important for your crime scene analysis. Ricochet crease, an impression or indentation in the surface resulting from a ricochet. Example, ricochet off an automobile hood. Now, as you know, most of our crime scenes outdoors, somebody's car takes a bullet, right, when we have these shootings, especially police involved. Quite often there's a lot of shots fired. So we have a ricochet mark. It's a mark left on a surface as a result of a ricochet. So a ricochet off of a windshield or glass. So ricochet mark versus a ricochet crease. Okay, the mark is going to be more two-dimensional. The crease is going to be three-dimensional. So another way to determine directionality is the V or funnel effect. So lead and lead-nosed bullets will usually leave a deposit of lead at the initial point of impact. And as the bullet continues to change direction, it makes more surface contact. A V effect is created by the ongoing deposition of lead. Right? So when you see this V shape right here, it's going to give us our direction of travel. You see our direction of travel here is from right to left. Okay, think it sort of radiates out, right? Creates this V shape. That's your point of impact. Your bullet's traveling right to left. Okay, here's an example, something that would kind of follow that. We have something else here. We have a little paint pinched right here. We'll get into that a little bit later. Right? Here's our V. Right? So the bullet struck here. One of the things you look for, you see how the paint gets scraped away in this area, right? But right here where the bullet made contact, there's paint. So some people call that a paint pinch, right? Where the bullet essentially pinches the paint between the bullet and the surface and then continues on its way and starts to dislodge the paint as it travels. But this point here still has the paint intact. So that's our pinch point. It's another way. What do we know? Once we know which side of the ricochet mark the bullet struck, we know which way it was going. Right? So deformed sheet metal, here's another way, right? So we have our pinch point, right? Paint gets pinched when the bullet strikes. And then we have these fracture lines also in the paint, right? Talking about sheet metal. Fracture line in the paint, lead splash could be possible depending on the configuration of the bullet. We have our direction of travel, left to right. So these lines are important. We're going to look a lot more closely at them. So effects of ricochet on painted sheet metal. What's our biggest source of painted sheet metal? You got it, the automobile. So the edges of flake paint off by a ricocheting bullet may give a clue as to the bullet directionality. Which direction was this bullet moving? We saw the previous example, right? These fracture lines, they go back towards the bullet, towards the impact point. Right? Think of the wake of a boat, right? So which way is this bullet traveling? Right to left. Okay, so what do we have here? Here we have a pinch point, and we have fractures going back like the wake of a boat. We also have a little depth to this. We'll get into that in a minute, but what way do you think this was traveling? As we discussed, you see those fractures in the paint, right? You can see it here. We didn't answer this question, right? Which way is this bullet traveling? It's traveling from upper right to lower left, right? Impact. Boom. Okay, so hopefully this is getting a little more obvious. We have paint fractures here. Bullet strikes over here. And we have our ricochet. These are some ricochets that I created off of some auto body parts. We can see that same sort of fracture line, right? In this primer. And the bullet where the bullet struck, boom. What we also have here is depth, right? So this bullet did ricochet. We have our impact point right here. As the bullet travels, it creates essentially a hole, right? It gets to the point where it's creating a crease that's so deep that the metal actually breaks away. So this end of the ricochet mark is deeper than this end, right? As we can see here, here's our impact point. As the bullet travels, it goes deeper and then it exits, right? So the entry point is more shallow than the exit point. We'll talk about that a little bit more. But yeah, so we go into those fracture lines, and as we can see, they're like the wake of a boat. So think about a boat traveling through water. And if you've never been on a boat, I feel sorry for you. Now, in case you're understanding what I'm saying, I'm going to confuse you. The underside, now when you think about processing a vehicle, sometimes it's really difficult to get a good look at something. There could be a ricochet mark where other damage happened or something where you're not really sure looking at the surface, the side at which the bullet struck, right? So sometimes it's not easy to determine directionality. You don't have enough of these characteristics to make a call. You can also look at the underside, right? So the underside of painted sheet metal can reveal bullet direction for a ricochet crease. Stress marks in the bare metal, paint flakes off underneath, will give the appearance of a Christmas tree, and the bullet direction is down the tree. So this is the underside. It's the exact opposite, right? Here's our fracture lines, right? We have those stress marks. And our bullet is traveling from left to right. So the key is to be able to get to the underside of a ricochet crease in painted sheet metal. As you know, it's very difficult sometimes. Sometimes you got to call people in, and the people that have all those tools, like we had in New York City, are some of the best people you're ever going to meet. But it might not be the most precise and forensically gentle type of cutting that they're going to do. They're just going to cut the thing out, and you have to get to the underside. So unless you have all the tools there yourself, you're going to want to get to the underside if you can't make a call on the surface that was actually struck by the bullet. So it's not always easy or even possible on automobile bodies due to obstacles such as braces or glass, etc., to get to these surfaces, right? So this is the underside of sheet metal that was struck by a bullet. See the Christmas tree, right? As you can see, we have no pinch point. It does look different. So what direction was this traveling? Down the tree, down the tree. Okay, the underside. Don't get confused. So what do we have here? We have these bullet strikes, right? If you got to a crime scene, you might say, hey, somebody really let a bunch of rounds go with a 9mm. And you look at, here's our impact side, nice symmetrical, and then there's a departure, but we're not really getting anything as far as rifling, right? This right here is symmetrical on both sides. So what we have here are double-aught buck pellets that were striking a concrete surface. One of the things that can be done here is you can go into a Photoshop program and draw an ellipse around this. And I'm not going to confuse you with trigonometry right now, but if you measure the width and the length and you divide the width by the length, you can determine an angle at which these pellets struck that surface. That's for another class. So the pear effect, that's another one, very similar to the V effect, right? So painted metal surfaces such as automobile bodies lose paint upon bullet impact, right? So more paint flakes off on the exit end of the ricochet. Makes sense, right? Paint flaking creates a pear-shaped area. Lead deposition, if present, indicates point of impact. More paint will be flaked off opposite the exit end of the ricochet crease. So here we have our pear effect. We have our pinch point, right? Lead deposit there. And you can see this is sort of pear-looking, pear-shaped. and we have our crease, and then around the crease we have our paint flaked off. Creates a pear shape. So, as I said, some of these can be called different ways, right? We have our pear shape here, which would give, we have our pinch point, right? Everything right now is telling us it's moving from upper right to lower left. We have our fractures in the paint. Right? Same thing with the wake of a boat. We have several characteristics. We also have increasing depth, going from upper right to lower left. So this should be an easy one for you if you get to a crime scene and you see this. Frangible surface. Remember that we were talking about that wonder board that I used, or sheetrock, right? So frangible surface, what is that? It's a surface that will break apart upon bullet impact, such as asphalt or concrete. Of course, we can use that as an example of a hard surface, right? But sometimes you have a road that's in bad repair, or driveway or something like that, where a bullet striking it will cause material to be dislodged upon impact and then create that ramp for the bullet to take off, right? So frangible substrate. So for frangible surfaces, the deepest part of the ricochet crease tends to be nearest the point of impact. Okay, that's the opposite of what I just told you for sheet metal, right? The deepest point of the ricochet crease will be nearest the point of impact. So now, if we have this ricochet profile, right, in a frangible surface, we can see the bullet came in, struck, created this little crater here, and it got more shallow as the bullet exits. So with a frangible surface, such as concrete and asphalt, the deepest part of the impression will be near the entry side. You can see to the left, that's a deeper part of the crease right there, left to right. Here we have our bullet striking the surface. Dislodging material, also known as spall. Right? The depth here is greater. It's the deepest point. And as it exits, we have a more shallow portion of this profile. Bullet metal transfers in the crater may be absent due to spalling and ejection of the impacted surface, right? So you might not have, say you want to do a sodium redizinate test on this, right? So the bullet strikes the surface, it breaks all this up, all this material, this concrete or asphalt or gypsum from the sheetrock or that wonder board material, whatever it is, it strikes there, it breaks it up. Now what's breaking up? This part of the surface that the bullet contacted. And then, so if we're going to look for trace metals in this, if we want to do like a sodium redizinate test and determine whether or not this is actually a bullet defect, the portion of this surface that has that trace transfer is actually being broken up and ejected. Spall, it's being thrown out of the profile. Okay, so keep that in mind. You might have on the exit side a possible lead splash. So these are things to look for. Non-frangible surfaces. Non-frangible surfaces do not break apart or fragment upon bullet impact. Instead, they bend or stretch. An example of a non-frangible surface is automobile sheet metal. Like I said, this is our go-to. Bullet ricochet creases in sheet metal can exhibit profiles where one end is deeper than the other. The deep end will be nearest the exit side, okay? Frangible surface, deepest end is the entrance side. The non-frangible, or sheet metal, automobile sheet metal, the deep end will be near the exit side. Okay, so here's another ricochet profile. Here's our surface. Before the bullet struck it, it would have gone straight across like this. we have a profile that gets deeper and deeper and deeper. So if this is a non-frangible surface like sheet metal, we're going to go by and we're going to use the depth of this crease, the profile of the crease, to determine which direction the bullet was traveling. Well, here it's much more shallow than it is here. So our bullet would have been traveling from left to right. That's our entry point. That's our exit point. Okay. As we can see in this photo that I actually did this one myself, we have our point of impact. We have our fracture lines that are going like the wake of a boat. We have a profile that gets deeper and deeper, right? So we have at least 3 ways to determine which way this bullet was traveling. We have at least 3 characteristics we can look at to determine directionality. Here's our classic ricochet mark, right? We have this symmetrical point of impact, our bullet direction, left to right. Okay, our classic ricochet mark. Can you see the lines here? Tell me what the rifling of the barrel this bullet was fired down is, left or right. Okay, if you sat the bullet on its base, stood it up, these lines are leaning to the right. We have a barrel with a right hand twist. Sometimes the ricochet mark will appear the same on both ends. When you see this, no directionality can be established on this alone. Don't be afraid to say these 3 words. I don't know. Okay. When you work these high profile cases, some boss is going to come up to you at the crime scene and say, hey, which way was that bullet going? And you look at it and you say, well, to me, it looks like it could be right to left. And then he runs to his boss, who runs to his boss. And then you go home that night and you're having a beer, saying, man, that was a tough day out there in the hot sun processing that crime scene. And then you see the commissioner on television saying, yeah, well, the bullet that struck this surface was going from right to left. And you're like, oh, man, I hope I was right about that, right? Sometimes you make a call. Don't be pressured into making a call. Your job is so critical, and precision is what we're after. The truth is what we're after, right? So sometimes you're going to look at something and you can't determine a directionality. And it doesn't matter how much brass is on the collar of the guy who's asking you. You say, listen, I don't know. Those are great words, 3 great words. I like to use it when I'm testifying. It's wonderful. Takes all the pressure off, right? You present yourself well. You say everything that you do know, so you're not a dummy. And when they ask you a question that you don't know the answer to, don't be afraid to say, I don't know. I don't know. That's a good question. I can look that up and get back to you, right? It's the best way to learn. If you're a know-it-all, how many know-it-alls do we know out there? All right, everybody raise your hand. Everybody's got their hand raised right now, right? So what happens with the know-it-all? You ask him a question. Of course, he's got the answer. Is it the right answer? Who knows? He's got an answer. He's a know-it-all. You can't learn anything if you think you already know it. So I don't know are 3 really great words. I like to use them all the time. How often? I don't know. So look at this one, for example, right? There's a couple things you might say, well, this could be this could be that. Like, I don't know works really well, right? I don't know. This one here, I don't know. It's a good question. You know, I actually fired this, so you see where the scale is. I can tell you now this bullet was traveling from left to right. If I walked up on this at a crime scene and I had everybody surrounding me, say, yeah, John, which way was this going? I don't know. Don't know. I don't want to make that call. This is a lot more obvious, right? We have our symmetrical impact point. We can tell right now Which way is this bullet traveling? You tell me. Left to right. What else do we know? It's fired from a barrel with a right twist. So ricochets off of glass. We're going to see plenty of those out there. At very low angles, ricochets may produce only marks on glass. No gouging, just a mark. These marks typically have the classic rounded edge at the point of impact. Here's our classic rounded edge. So which way is this bullet traveling? Left to right. Here's another way that you can tell ricochets off laminated glass, typically a windshield, at moderate angles will produce cracks consistent with the direction of force. These cracks often take on a jellyfish appearance. So here we have these cracks, this jellyfish appearance of the cracks, and we have an impact point. The cracks are giving us our direction of travel. Right? Left to right, going towards the cracks. Don't forget, ricochet marks and creases may bear rifling marks that are visible even to the naked eye. Be sure they are consistent in appearance, all towards one direction. This is true even for ricochet marks on glass, as long as there is no surface disruption upon impact. A microsil casting of these marks after detailed photos may assist a firearms examiner in determining class characteristics of the rifling or even make an ID. Okay, what did we talk about? Class characteristics. What do we have? Nike Air Jordan size 10, right? We have rocks lodged in the shoe. We have somebody walked across burning coals with that shoe. Guess what? It's not that type of shoe. It's that shoe. Right? Same thing. Class characteristics. The measurements between the marks of the rifling can give us class characteristics, right? It can tell us something about the rifling, the lands and grooves. Now, and also our rifling, left twist or right twist. But it could be so distinct that a firearms examiner can actually say, this is the bullet that created that mark, or whatever bullet created that mark was fired from this firearm. So that's pretty precise. Microsil can do a very good job out there. So what do we have here? We have our classic impact mark. We have a bullet traveling from left to right. We have more of the mark on the left side. Okay. What does this tell us? It's telling us the bullet's traveling from left to right, and it's fired from a barrel with a left twist. If you look closely, you can see some rifling marks. This is on steel. So determining the ricochet angle. All right, now how do we do that? That's a lot of work right there. Not something you're going to do at the scene. You're not going to pull out your service firearm, start shooting at the same cars. Hey, well, let's see where the bullet goes, right? So it is possible to determine ricochet angles through test firing using targets to record the impact of the ricocheting bullet. It is also possible to use tracer ammunition to visually track ricocheting bullets under test conditions, right? So not at the crime scene. Here's one way we can do it. We have this symmetrical mark over here. It's the same thing with the trigonometry that we talked about. This won't determine our ricochet angle. This will determine our impact angle. Okay, so we know when we look at this mark that the bullet's traveling left to right. What angle was the bullet fired at? This doesn't give us our ricochet angle. This gives us our angle of impact. So the bullet's traveling here, creates this mark and departs. We can calculate this angle. We just divide the width by the length. We take the arc sine of that, sine to the -1, and that'll give us our impact angle. Might not need any of this stuff. Right? Another way to do it, if you have a similar substrate and you have the same firearm type, or the same firearm, you have the same cartridge, the same bullet configuration, right? What we do here, we fire the bullet on, and we make contact with the substrate, right? And whatever our angle of impact is going to be. Of course, the bullet ricocheted. So what does that tell us, right? We're at or below the critical angle. I'm going to go back towards the beginning with you, mess with you a little bit. So the bullet strikes this substrate here. It ricochets here, creates a mark, right? If we level across from, and measure as well, from here to our witness panel, okay, this is a witness panel, we can take this measurement here, right? So if we, the point, the level point from this surface to our witness panel comes out to here, right? We have this distance, we take this distance, and now we have the distance from what's level between this surface and our witness panel, and then where the bullet struck. What do we have here? We have two legs of a triangle, right? I'm going to kill you again with that trigonometry. So we have two legs of the triangle. This leg here and this leg here. If we want the angle here, so then if I was going to draw my hypotenuse, I'd draw it from there down to there, right? From here to here is my hypotenuse, right? So these are two straight legs of the triangle. Boom, to the panel, then up from that level point. If I want this angle here, the angle at which the bullet departed this surface, I have my opposite leg of the triangle and I have my adjacent leg of the triangle. So what's that? Tangent, right? Remember SOHCAHTOA, right? Sine is equal to opposite over hypotenuse, right? And then we have tangent, TOA. TOA is opposite over adjacent, right? Ka is cosine equals CAH, right? Adjacent over hypotenuse. So we don't really use that one. We use a tangent and we use the sine. So now if I took, so we have tangent is TOA, opposite over adjacent, right? So if I take this measurement and divide it by this measurement, and I take the arc tangent of that, that's going to give me my ricochet angle, right? So the bullet's fired from up here somewhere, strikes this surface, and ricochets over to our witness panel. Are you going to need that for every single ricochet, every single crime scene? No. If you do need it, this is how you do it. Arc tangent, right? That's tangent to the -1. Here we have tracer bullets fired into sand, and we have the bullet ricocheting off to the right-hand side. What's that telling us? This is a right twist. Okay. And here we have the bullet ricocheting off to the left side. What's that tell us? This is a left twist, right? As I said, much less common than a right twist. But anyway, that shows us our angle of deflection. Here's a video I made firing at the hood of a car, right? Let's have a look at this one. There's our shot fired. And here is our mark on the witness panel, right? So here's the substrate or the surface that the bullet's going to strike. Here's our witness panel. From this mark to the mark on the witness panel, right? From our ricochet to our impact over here, we have deflection off to the left. I was firing a 1911 Colt with round nose ball ammo, and so the Colt has a left-hand twist. So we're getting deflection, right? The bullet strikes the hood here and gets deflected off to the left, as we saw in those photos. Okay. Quick story: I was at a crime scene one time when I had just learned this. Ed Heesky came to train us in bullet ricochets and crime scene shooting reconstruction, and we had a melee going on somewhere. We went to go reconstruct that and do our crime scene analysis. And I saw a ricochet mark on the sidewalk, and I could see that it was a right hand twist. And everybody who saw the ricochet mark, and people, we pretty much knew where the bullet was coming from, right? So it wasn't a matter of determining directionality. But now because we're processing the scene, we want to find the bullet. And everybody was looking pretty much straight ahead from where the ricochet mark was. And I saw it had a right hand twist. So I was off over here and I found it in the house. And I called Husky up and I said, "Hey, man, you'll never believe it." And he said, "You kidding me? This stuff works." So this stuff works. So how do we document ricochet marks and creases? Close-up photographs should be taken with a scale present. Right? Overall photographs should be taken with arrows present to denote bullet direction of travel. In order to document rifling marks, ricochet creases must be cast with a silicone type material such as microcell. Okay, might not be every time. You might not be able to see that, but so the overall is important, right? If all you do is go to your crime scene and you take these really nice close-up photos with a macro lens and your scale and all that, that's great. But later on down the road, sometimes these things go to trial a year, 2, 3, 4, 5, 20, 30 years later, and you see this beautiful photograph taken with all this detail, and you can see the fractures and the pain, you can see the pinch point, you can see all that good stuff. You can even determine a profile of the crease. You say, "Yeah, look at this bullet. We know it was going from right to left." But all you have is that picture. So what good does it do you? So if you have it, an overall photo of the vehicle or whatever the surface was, and then you show a directionality, and so we know now, okay, that vehicle that was part of the scene, we have a bullet that traveled from right to left. You can put everything into context. Okay, so remember, overall, intermediate, and close-up photos, very important, so we can reconstruct things later on. So let's test your understanding. For each of the following ricochet marks and creases, determine the directionality of the bullet that produced them. This is a test. Remember, if you can't find any good indicators, classify the directionality as inconclusive. All right, what do we got? Well, I gave you the answer on this one, right? Left to right. What about rifling? Somebody call it out so I can hear you. What's the rifling? Left twist, right? How about this one? What do we have here? Well, we have basically bare naked sheet metal, right? Not the band, the metal. So we have like a symmetrical portion of our crease profile. And as you look at it, it gets deeper. It also kind of flares out almost like a pear here. So there's a couple things we could look at. But we have sheet metal. We have a deep portion of our ricochet crease profile to the right. So what happens? What does the bullet do? The profile gets deeper as the bullet travels along the substrate. So here it's shallow, here it's deep. So in this substrate here, we can say the bullet's traveling left to right. How about this one? Don't forget the note down here. This is the underside of a sheet metal panel. The underside. Where does a bullet travel? Down the tree. Down the tree. Now here's the underside as well of some sheet metal. And you remember that ricochet that I showed you where the bullet created a hole in the substrate, but it's still ricocheted, right? So it creates this effect on the metal. And we can look at these as like fingers. They're pointing the direction. Bullets traveling. lower left to upper right. How about this one? What do we have? Well, as we look at all these defects in the paint here, we can tell they're pre-existing, right? We're not going to use them as part of our analysis. What do we have? We have sort of a V effect going, right? So upper right to lower left. Very similar right here. What do we have? We have a V effect. We have our pinch point, upper right to lower left. Okay, and here's the opposite side of the one we looked at with the fingers right now. We have sheet metal. We have our impact point. We have our crease getting deeper and deeper, right? Which way? I can't hear you. Lower right to upper left. This one we've seen before. What are our characteristics here? We have our fracture lines in the paint. We have a little paint pinched right here. We have our impact point. We have our direction of travel, wake of the boat, upper right to lower left. Same here is what we've seen something very similar to this before. Profile getting deeper, right? It's sheet metal, right? Not a frangible surface, so it's stretching as the bullet travels down it. So left to right. Okay. How about this one here? Well, if you go by where I put the scale, it's traveling right to left, right? But as we look a little closer, we can see some of the fracture lines in our primer, our boat wake. We have our paint pinched right here. We have our profile getting deeper, right to left. How about this one here, right? We have our symmetrical impact point from bottom to top. All three of these, what do they all show you right now? Our pinch point, right? Everything here, right to left. What else can we see? This appears to be getting deeper, right? These paint fracture lines aren't all that conclusive. Maybe you can see this going backwards a little bit, but here our pinch point is going to be the characteristic that's most obvious. How about this one? Looks like it was drawn with a pencil, but it wasn't. What do we have here? Give me some characteristics. What can I tell by looking at this mark? Right. We have our impact point. We have a mark that extends more on the left. So we have a bullet fired from a barrel, traveling right to left, and the bullet had a left twist. I'm sorry, the rifling in the barrel was a left twist. Okay. Here we have a wooden substrate. We have something very similar to the top of the laminate, gets pinched. We have a symmetrical impact point, right? We have a bullet traveling from left to right. Here's our fracture lines. Here's our pinch point. Here's our deeper side of the crease, right to left. Fracture lines. Profile of the crease, pinch point, right to left. Here's a close-up with a macro lens of some of the fractures. Might not be overtly apparent when you first look at it, but get a closer look. Bring out a magnifying glass like your Sherlock Holmes, right? Here's a ricochet off of a car seat, right? Can we apply some of these principles to this? Well, yeah, here we have our symmetrical impact point, right? Gets a little deeper over here, takes off. left to right. Closer look at that. This is a bullet fired into sheet metal, right? And we have our impact point on the witness panel, right? So I'm firing into this onto this sheet metal and creating these marks. What do we have? Right twist, left twist, left twist. Everything's going from bottom to top. So now here's the marks on the witness panel. What happens? We have like a bullet profile here, right? So this could be that the bullet is deformed, and also or the bullet's tumbling, right? So we're not getting a nice round mark on our witness panel. So after a bullet departs from a surface, it'll typically be tumbling. Depending on the surface, it'll be deformed usually, right? So these three, I believe, were done made with 45, and then we have something else. I was firing a 22 into that metal, right? So this is a 22 Magnum being fired at a very steep angle onto the into the steel, right? We have our impact points. So what do we know when the bullet strikes over here? Which way is it going? It's going that way, right? And this is from a 22, right? These are 45. This is a 22. That's how flat that thing got, right? Right here. Went through like a flying saucer. So I'll leave you with that one. Of course, they might not have been as knowledgeable about ricochets as we are, right? Because the sheriff, he's a smaller, faster moving uh, projectile, so less likely to create a ricochet. Thank you all very much. Appreciate your time.